Our topic today is rotational kinetic energy. First of all, we will define rotational kinetic energy. Energy possessed by a body due to rotational motion is called rotational kinetic energy. Mathematically, we can define rotational kinetic energy as half I omega square. In this equation, I represents moment of inertia and omega represents angular velocity. Now we will find rotational kinetic energy of a rigid body. First of all, we will consider a rigid body which is made up of n particles. There are n particles present in rigid body. We will calculate kinetic energy of all these particles. In order to calculate total rotational kinetic energy, we add kinetic energy of all these particles which are present in rigid body. We now tangential velocity is equal to r omega, where r represents the radius of circular path or circle in which body is rotating, and omega is angular velocity. So relation between angular velocity and tangential velocity is v is equal to r omega. For particle 1, we know kinetic energy is equal to half mv square. Since it is particle 1, so we write it as m1 and v1. From the above relation, we insert the value of v, and here we get half m1 r1 square omega square. Similarly, for particle 2, we get half m2 r2 square omega 2 square. This diagram shows an object, ith object or ith particle. By stating ith particle, we mean any particle present in rigid body that is selected for the analysis is shown to be rotated about an rotational axis AA. So kinetic energy of nth particle is half mn rn square omega square. In order to calculate total kinetic energy of all particles, we add up these kinetic energies, and here I have added all these kinetic energies. 1 by 2 is common among all terms. Similarly, omega is common among all terms. So we have taken 1 by 2 and omega square as common, whereas the terms inside brackets represents the moment of inertia of particle 1, moment of inertia of particle 2, and so on. At the end we get moment of inertia of nth particle. So when we add all these individual moment of inertia, we get total moment of inertia. So kinetic energy will be half I omega square. This is our desired relation which was to be derived here. Next, we consider an example of rotational kinetic energy in the form of a moving disk and hoop. So first of all, we will start with the disk, and then we will find the rotational kinetic energy of hoop, and we will see what is the difference between two. So this is the relation we have just derived. Kinetic energy rotational is equal to half I omega square. What we have to do is just insert the value of moment of inertia for disk in this equation, and we will get kinetic energy for a moving disk. So for a disk, moment of inertia is half mr square. A disk has the moment of inertia of 1 by 2 mr square. So we insert this value of I into above equation. Here we insert this value, and after simplification we get 1 by 4 mr square omega square. We know v square is equal to r square omega square. So we replace this r square omega square by v square, and this is the final relation for rotational kinetic energy of a disk, which is equal to 1 by 4 mv square, which is equal to 1 by 4 mv square. Now we come towards the hoop, and the moment of inertia of hoop is equal to mr square. Now we insert this value of I into rotational kinetic energy general formula, which is 1 by 2 I omega square. After inserting the values, this becomes half mr square omega square, and after simplification by placing r square omega square by v square, we get half mv square. This is the relation for rotational kinetic energy of a hoop. Now we consider an example in which we have placed a disk and hoop at the top of inclined plane. When we release this disk and hoop, they start moving downward. The potential energy at the top of the inclined plane is converted into the kinetic energy. Using this relation, we will find which of these two will be moving faster when they reach at the bottom of inclined plane. So we know the potential energy stored here will be changed into kinetic energy. So we can write potential energy is equal to kinetic energy translational plus kinetic energy rotational. We have two independent motions here. One is moving downward while the other is along their axis of rotation. So since we have two motions, we will have two types of kinetic energy. One will be translational or linear, and the other will be rotational. Here we insert the values of potential energy, which is mgh, kinetic energy is equal to half mv square, and kinetic energy rotational is equal to half I omega square. We have just calculated the kinetic energy rotational for a disk, which was 1 by 4 mv square. So we have inserted the value of kinetic energy for a disk here, and after simplification we get V is equal to under root 4gh by 3. The velocity of disk at the bottom of inclined plane will be equal to 4gh divided by 3 whole under root. The same process will be repeated for the hoop, and we have just calculated the kinetic energy of hoop, which was equal to half mv square. So after inserting this value, we will get the velocity of hoop here, which is under root gh. Now I will leave one task for you. Compare both these velocities, velocity of disk and velocity of hoop, and guess which one of these have greater velocity when they reach at the bottom of inclined plane. Thank you very much.